Hi, chemistry students. This is your Unit 12 lesson on some very special solutions called acids and bases, as well as defining what is pOH, and how we do calculations with them. The reason why this particular slide has lemons and soap is because they are very good examples, very common examples of lemon juice is an acidic solution and soap is a basic solution. Now you have notes that you're going to need to take, so if you actually have a packet of notes with guided notes, you may want to open to that and be ready to take notes. Otherwise, you can take notes as we go along, and please pause the video to make sure you don't miss anything. So here we go. All right, first of all, what is an acid? Let's just talk about the characteristics of acids. Acids taste sour. Now, you don't want to drink hydrochloric acid, just trust me, but there are plenty of acids that you do consume in everyday life, like lemon juice, that you know to be sour. So acids taste sour. They tend to feel kind of sticky on your hands. They're corrosive. Their pH, which we're going to talk and define later in this particular presentation, is less than 7. They tend to be very reactive, and many of them will react with metals to produce hydrogen gas. They are electrolyte solutions. They are substances that when you put them in water, because they're solutions, those solutions will conduct electricity. So they are electrolytes. Now, there are two kinds of indicators that we're going to talk about in this unit. Indicators are things that change color based on whether there's an acid present or a base is present. And the two indicators that are most important to remember are litmus paper, or sometimes it's just called indicator paper. Acids tend to turn it red, and something called phenolphthalein, which will remain colorless in the presence of an acid, but it has a real strong color for a base, so it makes it a good indicator of whether something's acidic or basic. Now, what about a base? And again, good characteristic base is soap. Soap, if you've ever had your mouth washed out with soap, tastes bitter. Basic things tend to make food taste bitter. They are slippery because they are literally dissolving part of your skin as you feel them. A strong base will literally take off your skin. A weaker base, like soap, might just wash off the dirt, but they feel slippery. Their pH is greater than 7. They tend not to react with metals. They do conduct electricity. They are also electrolyte solutions. So when you put a base into water, make a basic solution, it will conduct electricity. Ions will be present to conduct the electric current. In terms of the two indicators, base, a lot of B's here, bases taste bitter, and they turn indicator litmus paper blue as opposed to red for acids. And they turn phenolphthalein a really pretty color. It's called magenta. It's kind of a purple color. So unlike acids that stay colorless, phenolphthalein will turn purple in the presence of base. Okay, moving on. So we want to be able to identify by looking at the formulas acids and bases. And acids really have a tell. How can you tell if it's an acid? Well, take a look at these acids and see if you can see what is the common between all these acids. So here is sulfuric acid, a very common acid. If you take more chemistry, you'll have to memorize this formula. H2SO4 is sulfuric acid. HNO3 is nitric acid, HCl is hydrochloric acid, H2CO3 is carbonic acid. Now there are these things called organic acids. They have carbon and hydrogen in them, all of them, and this is acetic acid that's found in vinegar. It's oftentimes written with this H on the end, but sometimes it's written with the H on the beginning. So this is either one of these could be a formula for acetic acid. Now what do you notice about all these formulas? What is in common? What you'll notice is in common is that all of them start with hydrogen. And that hydrogen, even though it is covalent, when it gets into an acid solution, acts like a 1+ ion, kind of like an alkali metal. It actually dissociates, even though originally it is covalently bound in these substances. When you put them in water, the hydrogen ion breaks off, dissociates, and forms and floats around in the solution. So you can tell an acid by seeing this hydrogen and that first cation location. The hydrogen ion is an indication that this is an acidic solution. Okay, how about bases? Let's see if it has a tell. So here are 3 very strong bases, things that make things very basic, very high pH, pH 14. Sodium hydroxide, potassium hydroxide, magnesium hydroxide. I bet you noticed a similarity. Every single one of them has hydroxide in them. And so in strong bases, you will find in their formula the OH 1- ion hydroxide, as compared to acids where you find the H+ ion. Now, we do, unlike acids, we do have another way of generating a hydroxide, OH 1-. And these bases tend to be called weak bases. Two bases that you don't see hydroxide in are ammonia and baking soda, the bicarbonate ion in baking soda. And when you put these in solutions of ammonia or baking soda and you test them with indicator paper, it turns it blue. It's a base, but where is the hydroxide if bases have hydroxide? Well, ammonia and baking soda can actually steal hydrogen from water. So when you put ammonia and make a basic solution with ammonia and water, essentially what happens is it takes a hydrogen from the water, remember it's H2O, and leaves behind a hydroxide. So even though you don't see hydroxide in the formula for this base, ammonia, or in the formula for the bicarbonate, what they do is essentially generate hydroxide by taking a hydrogen ion from the water and leaving behind hydroxide. So they too are bases. They are still bases because they generate the hydroxide ions when they react with the water. Okay, now in a video that you saw in my class, they talked about two different definitions of acids and bases. And these are based on the work of a couple of scientists of trying to figure out what makes something acidic and what makes something basic. Now, for the acidic side, Arrhenius, who was the first one to try to define what an acid was, and then Bronson and Lowry, they're very, very similar. It hardly tell the difference. It's a matter of words, and these words are going to make a difference when we start talking about bases. But if you fill in your chart for an Arrhenius acid, they produce hydrogen ions in water. That's why it's in the formula. The HCl dissociates into hydrogen and chloride ions. The formula starts with an H. An example is hydrochloric acid. When we put it in water, it breaks up into hydrogen ions and chloride ions and adds hydrogen ions to the water. Now, a Bronson-Lowry acid is very similar, but we have a different way of expressing it. We donate hydrogen ions. They're called proton donors because a hydrogen ion is just a single proton if you think about it. They actually add protons to the water, and the water actually will take it and become something called a hydronium ion. But they donate. We like to use the word donate. They're donating, not just producing it, they're donating it to the water. Again, their formulas start with H, and pretty much Arrhenius acids and Bronson-Lowry acids are pretty much the same. Hydrogen in the formula, hydrochloric acid is also a Bronson-Lowry acid. Now, when you get to bases, the language makes a difference. So let's look at bases. So Arrhenius had a very narrow definition of base. It had to have hydroxide in the formula, like sodium hydroxide, potassium hydroxide. They produce hydroxide ions in the water. An example of that would be sodium hydroxide. But the problem was there were certain things that acted like bases, like ammonia, that didn't have hydroxide in the formula. So Bronson and Lowry kind of expanded the definition. And they called bases proton acceptors. So literally, the ammonia steals a hydrogen ion from water, leaving behind the hydroxide. So they take a hydrogen ion from the water, and again, a hydrogen ion is a proton, and so they accept it. The proton adds on to the ammonia, leaving behind the hydroxide. So we call a Bronson-Lowry base a proton acceptor rather than something that generates hydrogen ions. We take a hydrogen ion from water, leaving behind a hydroxide. So that's why something like ammonia can be considered a base, and it is a base because it makes litmus paper blue. Okay, so this is just something we're going to touch on this year very briefly. You'll do more of this in your AP or IB Chem courses, but there are these things called conjugate acid-base pairs when we talk about Bronson and Lowry. So let me show you an example. So here is an acid, a classic acid. It's a sulfuric acid, H2SO4. We call the acid-base pair a conjugate acid-base pair. So it differs by a hydrogen ion. So acids can donate hydrogen ion, and what's left behind, this HSO4, is what's lost it. It's called the conjugate base of this particular acid. So the difference between a conjugate acid and its base, and we'll see this when we look at the equation a little bit more, is that is a single hydrogen ion. The acid has it. It's able to put it into the water. The base can accept it. And so this would be the conjugate base. So look at this pattern here and look at these equations and see if you can fill in for H3PO4 and HF. What would the acid be that would go along with this base? And you can kind of see it here. Pause the video, take a guess. I'll show you in the next slide. So here are the conjugate acid-base pairs. You can note that the difference between them is that hydrogen ion. So in this particular conjugate acid-base pair, HF, hydrofluoric acid, is the acid. It has a hydrogen ion that it can donate. The base, it can accept a hydrogen ion if it needs to. And so it's the conjugate acid-base pair. So when we have, for example, ammonia reacting with water to give us a basic solution, we have an example of an acid-base reaction where we have conjugate acid-base pairs, where something is accepting and something is donating. And so what you can see here is we have ammonia, which is our base, and we're going to classify water as our acid because it has an extra hydrogen ion it can donate, okay? So in this reaction, water donates its hydrogen ion to the ammonia, leaving behind the hydroxide. So it's acting as an acid. Weird, right? It's acting as an acid, so it can donate its hydrogen ion. And so its conjugate base, that thing without the hydrogen ion, is this, is OH1 minus. They just differ by that hydrogen. Now, what has happened to that hydrogen? Well, this base can accept it, so that's why it's a base, and the conjugate acid that has accepted it is this ammonium ion. And again, notice the base has one less hydrogen. Now, understand why I have a +1 here. The conjugate acid has accepted a H1 plus ion. That's why overall it has a 1 plus. The water has lost a 1 plus, and that's why what's left behind is a 1 minus. But notice these conjugate acid-base pairs. Let's look at one more. Here's one where water, weirdly, water can act as an acid or a base. Here we have an acid. We know that because of the hydrogen here. Okay, it can donate it. It donates it to the water this time. And water forms something called a hydronium ion, and it leaves behind Cl1 minus, okay? So we are donating the hydrogen and leaving behind the base. And again, the difference between an acid-base pair, it's essentially the same species, just differing by one hydrogen ion. So this is the acid. Cl1 minus would be the weak conjugate base. Water is something called amphoteric, and it can act as either an acid or a base. And again, in this case, it's a base because it can accept a hydrogen ion to form this hydronium ion, which is going to make the solution more acidic. All right, so just to summarize here, the difference between the two definitions. Acids yield hydrogen ions. They'll be in the formula. Bases in Arrhenius definition yield hydroxide and will be present in the formula. For Bronsted-Lowry, yield and donate are very similar. So Bronsted-Lowry, though, are called proton donors. They have an extra hydrogen they can give away, and bases have room to accept a hydrogen. And so from water, you'll leave behind, if it's a basic solution, OH minus, so they're proton acceptors. Okay, now let's get to the mathy part of this. We're going to talk about pH. What does pH measure? You probably are very familiar with pH being a measure of acidity. But what is acidity? Acidity is a measure of the concentration of hydrogen ions. Acids tend to donate them to the water. Bases tend to take them away. Now, concentration, remember, is measured in molarity, and hydrogen ion concentration in acids tend to be really small. like 0.01, 0.001, 1 times 10 to the negative 15. So scientists don't really want to use those long things. What's the acidity of this? Well, it has a hydrogen ion concentration of 1 times 10 to the negative first, therefore it is acidic. They use a definition that is useful for shorthand because we're lazy, okay? So the definition, the mathematical definition of pH is the pH equals the negative log of the hydrogen ion concentration. These brackets mean concentration, and we're going to see how that is. Now, there's some easy way to do it if it is an easy number, but you may have to use your calculator for some of our calculations here using the log button. But let me show you the easy way. Remember, log is a base 10. So what it means in terms of pH 1, what does that mean? We say pH 1 and we say that's real acidic, right? So what that means is that the hydrogen ion concentration is 1 times 10 to the negative first molar. Now remember what that is as a decimal. That's 0.1 molar, because that's the same thing as 1 times 10 to the negative 1 molar. Notice the pH is just the exponent, okay? If it's 1 times 10 to the negative 3 molar, that's pH 3. pH 3 is less acidic, right? It's closer to neutral. And that's because we have less hydrogen ion. This one is 0.1. This one is 0.001 molar, 1/1000th, okay, as opposed to 1/10. 1 times 10 to the negative 7 is the pH of neutral water, and we'll talk about why that is in a slide or two. And 1 times 10 to the negative 10, so very little, teeny, hydrogen ion concentration is pH 10, and something that has very low hydrogen ion concentration tends to be a base, okay, because pH 10 is the basic range. What are typical pH values? You may be familiar that neutral is pH 7. Acids tend to be 1 to about 6.99, okay, like really neutral is 7. Really acidic is 1. Only slightly acidic is the closer you get to 7. And that's because you're getting, as you get towards 7, you're getting less and less hydrogen. And things that are acidic have lots of hydrogen ion in them. So that would be pH 1. Bases tend to have very little hydrogen ion, and so their pH values tend to go from 7.01 to 14, and then neutral has this number that I'm going to explain here in just a minute of 7. Okay. All right, so the reason why we have the scale in this parameters is because this is generally the kind of solutions you find out in nature. You don't find anything that is less acidic or more basic. You can see that it runs from battery acid, which is pH 0, which is essentially 1 molar, 1 mole per liter with hydrogen ions, all the way to drain cleaner, which is very basic, which has very little. Think about point with 14 zeros, 1 molar. And that's what causes us to have this range. You can have negative pHs like 10 molar, but that's like really concentrated acid. You don't really find this out in nature. You find all of these things out in nature. Okay, so let's actually do this in our calculator. So if I were to ask you to calculate the pH of a 0.01 molar hydrochloric acid solution, you would put into your calculator negative sign, then log, and then in parentheses 0.010 molar. And your calculator would spit out the number 2. You'll notice that 0.010 molar is also 1 times 10 to the negative 2, so the pH is also the exponent. This is very acidic. We have a lot of hydrogen ions. That makes sense. Now, what if, though, it's not a 1 times 10? What if it is a 0.03 molar hydrochloric acid solution? Again, you're going to want to get your calculator, negative, log, put in 0.03, parentheses, and you should have the calculator spit out 1.5. This makes sense. 0.03 molar has more hydrogen, is more acidic than 0.01 molar. That's why the pH is lower. It's more acidic. But it's not a whole number this time because we have it's 3 times 10 versus 1 times 10. Okay? We're going to get more practice on this later, but that's how you use your calculator to figure out the pH. It's shorthand. Rather than saying this is acidic because the hydrogen ion concentration is 0.03 molar, you would say this is acidic because the pH is 1.5. Okay? Now, think about the pH scale, though, for a minute. It is a logarithmic scale, which means pH units are different by powers of 10. So an increase in one pH unit, like going from 1 to 2, is going from 0.1 to 0.01, from 1/10 to 1/100th moles per liter. And so an increase of one pH unit would be 10 times less H plus. So you're going from 1, which is 0.1, to 0.01, going from 1/10 to 1/100th moles per liter. So pH 2 would be 10 times less than pH 1. A decrease, like going from 2 to 1, would be 10 times more. Okay? Now think about this as a logarithmic scale. If 1 is 10 times less or 10 times more, what would 2 be? Okay? All right? So what would 2 pH units be? So remember, what's pH 1? It's 0.1. What's pH 2? It's 0.01. It's 1/10, then 1/100th, and pH 3 would be 1/1000th. So it's not going to be 20 times. That's a big mistake people make. You're essentially raising that 10 to the however many units, okay? So it's 10 to the second difference between, say, pH 1 and pH 3. So it's 100 times less. Remember, you're getting less acidic as you go from 1/10 to 1/1000th. What would an increase of 3 pH going from pH 1 to pH 4? It'd be 1,000 times less because you're going from 0.1/10 to a 10,000th. Okay, so it's going to be 3 pH. It's going to be 10 to the third. All right. Now, kind of like, why is neutral water pH 7? Why does it have a hydrogen ion concentration at all? It's because water, even though it is covalent and shouldn't break into ions, does. A very small amount does. In fact, if you have a liter of water, most of it, 99.9999999% of it, is going to be H2O. But 1 times 10 to the negative 7th moles of it is going to be a dissociated form. It's going to put that much hydrogen into the water. It's going to break up into one hydrogen and one hydroxide. Think about it. When you put that together, that would be these two would be H2O. So at room temperature, it's 1 times 10 to the negative 7th. So however much hydrogen you have, that's how much hydroxide you have as well. And so that's the concentration. That's how much breaks up. And because it has 1 times 10 to the negative 7 hydrogen ions, that's why the pH is 7. Okay, but remember, the OH is going to be the exact same amount. There's a balance between the two when something is neutral. So what happens in an acid solution? In an acid solution, you add something, remember, that donates hydrogen ions. You raise the hydrogen ions and you lower the hydroxide relative to that. So in an acid solution, you've added something that gives you more hydrogen than hydroxide. You're no longer equal like you were in a neutral solution. You've added something that raises the hydrogen ion concentration. That causes it to be acidic. What happens in a basic solution? Think about the formula of a base. You add something that adds hydroxide instead. That will lower the hydrogen ion concentration. The hydroxide will dominate. And so in a basic solution, you have less hydrogen and more hydroxide. That's the out of balance. In a neutral solution, as I said, because you haven't added anything to offset the balance, it's going to be equal. All right, so let's do some calculations. You got to see my dog here. All right, so it can be shown at room temperature, because each can dissociate 1 times 10 to the negative 7th molar, that the hydrogen ion concentration and the hydroxide ion concentration is always going to multiply to 1 times 10 to the negative 14th. But that's a lousy number to have to play around with. And remember, we use pH as a shorthand, and pH is the negative log of the hydrogen ion concentration. Well, there's also a term called pOH, which is the negative log of the hydroxide concentration. So it can be shown that a neutral solution, and in all solutions, there's going to be a balance between the two. So these two concentrations multiplied are always going to be 1 times 10 to the negative 14th, which means that the pH plus the pOH are always going to equal 14. Let's see how we can use a chart to do that. Okay, so let's try to fill in this chart after I go through the examples here. Okay, so you're going to fill in below. But here's how everything relates. So here's the hydrogen ion concentration. It's 1 times 10 to the negative 12. And remember, if it's a 1 times, we can just use the exponent. So the pH of this solution is 12. pH plus pOH is always 14. You can fill that down the line. So if the pH is 12, the pOH has to be 2, which means that the hydroxide concentration has to be 1 times 10 to the negative second molar. That's more concentrated hydroxide than the acid, very little hydrogen ion. I just usually, once I figure out the pH, remember the pH scale, anything over 7 is a base, and I have more hydroxide in terms of the concentration. Let's look at the acidic one. 1 times 10 to the negative 4th means the pH is 4. That's an acidic pH. Means the pOH has to be 10 because it has to add up to 14, which means the hydroxide has to be 1 times 10 to the negative 10th. Okay? And that's acidic. Now here's neutral. Notice they are equal. Acidic, you have more hydrogen. Basic, you have more hydroxide. That's what defines it. Now see, you might want to pause the video and see if you can fill in the blanks here for the rest of these using the information that you know. You may want to pause the video, but I'm going to show you the key right now. Okay, so here is the key. And you can see in each and every circumstance, the pH plus the pOH equals 14. I use the pH to remind myself this is acidic because it's less than 7. I can see I have more hydrogen ion than I have hydroxide, and that the exponents here just are the pHs, okay? The negative exponents there. Let's look at this one. This is a very acidic solution because this is 0.1 molar versus very little hydroxide. Remember, 1 times 10 to the negative 13, it's a really small number. It's acidic, it's a pH 1. pH plus pOH equals 14. So check your work here. And then we're going to go to just the slightly more challenging one, the one where you have to use your calculator. All right, so this one you're going to have to use your calculator. And for these, you're going to have to kind of reverse the log. So you're going to use the 10 to the x button on your calculator and put the negative exponent in. Then you should be able to get your hydrogen and then your hydroxide. And again, remember, this is always going to be 14, and we can already see that 10.5 is going to be basic, right? So these are always going to be 14. So pause the video and see if you can do it, and the last slide will be the key. Oops. Here we go. And here is the key for you to check. Okay, so you can see we've got things over 7. These are going to be basic. This one is going to be acidic. Notice these all add up to 14. And if you were to multiply these two numbers together, you would find that they multiplied out to 1 times 10 to the negative 14. So good luck.